Hello, my name is Roy Simpson. I am a professor of mathematics at Cosumnes River College in Sacramento, California. This lecture I'm going to focus on systems of linear inequalities. Systems of linear inequalities, really we have to start with just a discussion about linear inequalities to begin with, kind of a review, and then we'll go into what a system of linear inequalities is. And at this point, you should have already had a background with graphing linear equations and systems of linear equations and solving systems of linear equations. You should know everything about slope, y-intercepts, x-intercepts, all that stuff. So we'll go ahead and start with a linear inequality in two variables. We'll define that. A linear inequality in two variables is just like a linear equality in two variables. Recall that a linear equality in two variables is like ax plus by is equal to c. But instead of being equal, we have an inequality. So in other words, we have something like less than or equal to, or greater than or equal to. So those are all inequality symbols. In fact, there's another inequality symbol, but I'm not going to write it down. It's the not equal to sign. However, we're going to deal with these kinds of inequalities, greater thans and less thans and whatnot. So that's a linear inequality in two variables. Very quick example would be something like 3x minus y is greater than 10 or something like that. Now, just like a linear equation, with linear equations in two variables, there's more than one solution. So in other words, if I wanted to find out the solutions to 3x minus y is equal to 10, there's an infinite number of solutions. And the way I can visualize those is to graph that. I would solve this for y, and I'd have something like this, and I'd see, oh, it's a line with a y-intercept of -10 and a slope of 3. So it looks something like that, roughly. Okay, that picture is a visualization of all of the solutions to that equation. With a linear inequality, not only do we have an infinite number that might lie on this line, but we have an infinite number of solutions that might lie elsewhere. In fact, let's go ahead and make a strict definition for the solution set of a linear inequality in two variables. We'll say that if we're given something like ax plus by is less than c, or it could be greater than c, or less than or equal to, or greater than or equal to, whatever it is, the solution set is the set of points on the Cartesian coordinate plane such that when substituted into the inequality, they make the inequality statement true. And that's kind of a plain Jane definition. It's nothing really crazy here. It just means that if a point xy satisfies this inequality, then it's in the solution set. It turns out, though, that the solution set to a linear inequality, in two variables that is, when you graph it, it ends up being a half plane. So let me write out a definition for that. And actually, as I started kind of writing this down, I thought, well, half plane, the only definition I can give for it is half a plane. I mean, it's like take a sheet of paper and draw a line over it. It doesn't even have to be half of it, actually. I didn't have to draw it like that. I could have drawn it like this, okay? But the fact is it separates this piece of paper into two sheets. This is called a half plane, and this is called a half plane. Okay? Even though it's not half of this paper, in mathematics, the planes that we deal with are infinitely large. So no matter where you draw the line, it splits the world into half. And finally, this line right here, and let me go ahead and draw an arrow to it, that line that splits the world in half that we use to create our half planes, we call that the boundary line. And there are a couple forms it's going to take when we start doing examples. Actually, there does not need to be an S on that. It's one of two forms. If it's less than or greater than, but there's no equality there, it's a dashed line. So that implies dashed line. And that's our way of indicating that our solutions can't exist on the line because they have to either be over the line or underneath the line, but they can't be on the line. The other case is if we have equality. right? If you can actually equal that line, if you can land on that line, then we go ahead and just do a solid line like we would when graphing a regular old line. So let's do an example here to kind of see what I'm talking about, because this was a lot of definitions and kind of conceptual approach to this, but it's much better to actually see this in action. I'll just turn the page here and I'll create some example. Let's go ahead and graph the solution set to y is greater than 2x plus 7. Now I know if it was y equals 2x plus 7, it would just be a nice line with a y-intercept or a vertical intercept at 7. So that's the vertical intercept. And with a slope of 2. So let's just pretend for now, just for this example, that this point right here is 0, 7. And then we're going to use the slope to get to another point. So I'm going to rise 2 and run 1. So let's just pretend that that's this point right here. So we ran 1 and we rose 2 points. So we're at 1, 9. And normally I would connect that, if this was an equality, y equals 2x plus 7, I would connect that with a line. So normally I'd have something like this. However, this is not an equality. It's an inequality. So I can't do that. Instead, I have to connect these 2 points with a dashed line. It's strict inequality and means that we can't actually be on this line because we have to be, well, y has to be greater than, strictly greater than 2x plus 7. Now remember, I told you this line is going to break the world into halves. We'll have one half that will be our solution set, and the other half will not be our solution set. The way you can determine which half is your solution set is to pick a test point. So pick a test point. And an easy test point, make sure you pick a test point that's not on your line. Okay? An easy test point is 0, 0. If the origin is not on your line, so this point right here, if that point 0, 0 is not on your line, go ahead and pick that point. It's a very easy point to pick. So let's try 0, 0. If you plug that into the original inequality, you get this. 0 is greater than, and I usually put a question mark here because I don't know if it is, 2 times 0 plus 7. So the question is 0 greater than 7? Right? Because that's what the right-hand side equals. And the answer is no. So that means that that point is not in the solution set. Let me write that down. So 0, 0 is not in our solution. And that's a huge piece of information, because to say that this is not in our solution means that the other side of this region, other side of this boundary line, must be our solution set. All the other stuff over here has to be our solution. And this is why we call our solution set a half plane, because half the world gets shaded. That's what I'm essentially doing, is I'm shading half the world. And all those lines there are basically me scribbling in and shading this in. Okay? So that means that everything there is in our solution set. You could try out a point to see if it's true. Try out any point that you think lands in this region, like a negative 10, 10. So a negative 10 means go back 10 and up 10. So let's try to see if that will make this inequality true. Plug in negative 10 for x and a positive 10 for y. Well, the right-hand side is negative 20 plus 7 is a negative 13. Is it true that 10 is greater than negative 13? Oh yeah, sure is. So that's definitely one of our many, many, many solutions, our infinite number of solutions. Okay? So when you graph a linear inequality, the steps are really just to graph the boundary line first. So graph it like it was an actual line. Make it dashed if it's strict inequality like this is, make it a solid line if there's an equals, or greater than or equal or less than or equal, and then choose a test point. And if your test point works, then you shade that side. If it doesn't work, like in this scenario, then you shade the other side. So let's go ahead and try another one here. Let's go and graph the solution set to the inequality negative 2y minus 3x is less than or equal to 5. And the first thing I'm going to do is draw a set of axes and graph the line first. So here's my x-axis, here's my y-axis. And the easiest way, if somebody hands it to me in this form, is just to find the intercepts. When x is 0, so make that negative 3x disappear, you get negative 2y is equal to 5. I know it's not really equal to 5, but I'm just trying to find the intercepts here. So when x is 0, you get that y is equal to a negative 5 halves. And along the same lines, when y is 0, you get that x is equal to a negative 5 thirds. So let me plot those points so you can see them. So 0 comma negative 5 halves might be down here, and negative 5 thirds comma 0 might be like right here, something like that. And now what I'm going to do is connect those 2 points just like it was a line, but I have to make certain that I'm using the right kind of boundary line. Since we have the equality here, that's less than or equal to, this will be a solid line, just like we were graphing a regular old line. And again, what I'm going to do is pick a test point to see which side of the world gets shaded. So let's let our test point be 0, 0 again, because again 0, 0 is not on our line, so it's a very convenient point to pick. If your line did happen to go through 0, 0, you could pick any other point that's not on the line, but like I said, 0, 0 is very easy. So I'll plug 0 in for y and x. I get the following: 0 minus 0 is less than or equal to 5. Is that true? Is it true that 0 is less than or equal to 5? Yes, it is. So this point right here is in our solution set, which means that our solution set must be this side of the graph or of the boundary line. Okay, all that half plane is our solution. And by the way, all the way up to this boundary edge. Now, something I have to mention, for those who use an online homework system like my students do, when you're plotting on an online homework system, just as a heads up, I usually don't talk about the online homework systems if you are watching one of these videos. But if you happen to be using one, specifically WebAssign or MathLab, MyMathLab or something like that, do not plot points. The reason why is when you plot a point like this and this, okay, the computer will think you mean that those 2 points are part of your solution set. In reality, those, like on this, for this example, remember this boundary line, you couldn't land on this boundary line because you had to be strictly greater than it. So when you plot these points, these solid points right here, a computer will think that you mean your solution can actually land on one of those 2 points as well. And it can't, because you can't land on that boundary line. So just to let you know, specifically if you're using a homework system like WebAssign, that you would graph this dashed line without plotting points first. Okay. Most people can ignore that whole conversation there. Now here's an interesting example. I like to sneak this into my classes because I think this is a great way to graph linear inequalities if you can do it. There is a logical way to graph a linear inequality without using a test point. If somebody gives me an inequality where it's like y is less than something or y is greater than something, or y is less than or equal to or greater than or equal to, as long as y is isolated, okay, like it is here, then I can use a little bit of logic to graph my half plane. The first thing I'm going to do is just go ahead and graph the line itself. So I see the y-intercept is here at 1, and I'm going to rise 1, 2, and run 1. Okay. And remember, when I connect those 2 points, because it's a strict inequality, so there's no equality there, it's not less than or equal to, I have to dash it. So let me just do that. And let me just show you how to figure out which side to shade without picking a test point. Here's how I generally have always read equations. The y, I generally say the heights. That's what y values are. They're the heights. So y is less than 2x plus 1. 2x plus 1 I consider to be the line. So the heights are less than the line. I'm having a hard time writing. So the heights are less than the line. So I want all my y values, or all my heights, to be below this line. Well, if you think about that, that's all this stuff down here. Everything down here is below, underneath this line. So this is my region that I would shade. If you pick a test point, you'll find out that this is actually true. You can do this all day long, making up examples that will illustrate this. Y is greater than or equal to, let's say, 3 halves x, let's do minus 4 or something like that. Well, y-intercept is negative 4, and then I'm going to rise 1, 2, 3, and 1, 2, 3, there we go, and run 2, and I'm going to connect those with a solid line because it's greater than or equal to, and then I'll ask myself, when are the heights above this line? When are my y values above this red line? Well, they're above this red line in this region, so this must be the region that gets shaded. It's a really quick way to graph things, but the only time you can do it is when you have y by itself on one side. Okay, so it's a very nice method. But otherwise, you could always pick a test point. That always works as well. Every once in a while, you get this oddball-looking equation or inequality. Graph x is less than or equal to a negative 3. Well, here's my x and y axes. Remember that for a line, x equals a negative 3, that's a vertical line at negative 3. So here's negative 1, negative 2, negative 3. And so I'm going to draw a vertical line. It's going to be solid because it's less than or equal to. So let me go ahead and do that. I have a solid vertical line. And I want to know, when are my x values less than that? In other words, try some values like x equals negative 4 is one of those. X equals negative 5 is one of those. And actually, it doesn't really matter what y is, because all these points that I'm clicking on right throughout here all have x values that are less than negative 3. So to shade that area, you just do what you did before. All this stuff has x values that are less than negative 3. You can do the same thing for y values, actually. Let me go ahead and get a new piece of paper here. I could ask something like, graph the solution set for y is strictly greater than a negative pi. Remember, pi is just some number, so it's not a variable, it's a number. And it's about negative 3.14. It's not really negative 3.14. I'm sorry, pi is almost 3.14, but it's not really 3.14. But a lot of students think it is, but it's not. It's approximately that. But this is going to be a horizontal line at a height of a negative roughly 3.14. So let's just pretend that's negative 1, negative 2, negative 3. So it's somewhere around this height. And remember, it's a horizontal line, and it's going to be dashed in this case because we don't have equality, so we can't land on that horizontal line. I'll just go ahead and graph it out really quickly. Not the best graph in the world, but it'll work. And the question is, when are my outputs, or when are my heights above that line? Well, here. That's where they're above that line. Okay, so all this area, I could shade it using a highlighter, I suppose, but you get the idea. Okay, so you can have an inequality that's a horizontal half plane, or basically an inequality with a horizontal boundary line or a vertical boundary line. Now, the title of this section was solving or graphing linear systems of linear inequalities, and we haven't even done a system of linear inequalities. But it turns out that they're not so bad. All it is just graphing two inequalities at once and shading their common area. So let me write that down actually. To graph a linear inequality, and maybe I should have said a system of linear inequalities, and you graph all the inequalities in the system and then shade the common overlapped region. Because you have these half planes that are going to be shaded everywhere. You want to shade the one section that is an overlap of all of their shadings. There's a hard way and an easy way to do this. Let's just do this the easy way. So let's go ahead and create an example. And I'm doing a very simple example at first, but still one that often gets ignored. We have a system of linear inequalities. They're lines because the powers on the variables are 1. They're inequalities because, well, they're inequalities. There's no equal sign. And the first one I'm going to graph is x being greater than a negative 3. So remember, x equals 3 is a vertical line at x equals negative 3. So let me go ahead and draw that in. And by the way, we can't exist on this vertical line because it is strictly greater than. There's no equality there. Let's do this. And I want all my x values to be bigger than this line. In other words, I'm looking at x values of like negative 2 and negative 1 and 0. So I'm going to sort of shade in this direction. The way I do it is I usually make a small little note here. This is like a comb almost, where you're basically saying that's the area, that's the region you would normally shade. I see students that go nuts here and they shade everything. Don't do that. Not with a system of inequalities, because you'll have a mess in the end. Now I'm going to graph the other one. Y is less than or equal to 4. So first thing I'm going to look at is y equals 4. That's a vertical line at a height of 4. I'm sorry, a horizontal line at a height of 4. It's a horizontal line, and I know that that I can actually equal that line. So it's going to be a solid line at a height of 4. Here's my solid line. Keep going with this. There we are. And it goes on in both directions, obviously, like the other line did. And I want all my y values to be below this line. So I'm going to shade in this direction. And again, I don't go crazy. I'm just going to initially just do this, and you don't have to do that many comb marks. I mean, I'm doing this because I want you to see that. Well, I'm sure you could see it even if I didn't take my time. Okay. Now you have to now ask yourself, what's the region that they commonly would have shaded? I'll number these 1, 2, 3, and 4. In region 1, neither of them are shaded, so that's out of the question. That's not going to be part of their solution set. In region 2, it'll have a red shading but not a blue shading, so that's out of the question. In region 3, I'll get a blue shading and a red shading. That's the good one. In region 4, I only get a blue shading, but the red doesn't come over here, so that's out. So the winner is region 3, and now at this point you can go crazy if you want and shade just that region. I will maybe do this one. This is the region. Okay. Okay, so there's my solution set. That's how you graph a system of linear inequalities. Now that's just one example, so I should probably do a few more so you can see what's going on, and also to kind of get some experience with it. But notice that a system of linear inequalities, you can have some boundary regions that are solid and some that are not. It's very common. For a less trivial example, we can take a look at this system of linear inequalities. We're going to go ahead and graph 2x plus 3y is greater than or equal to 12, and then 5x minus 12y is strictly less than 60. Again, I'll just do a rough graph here. This is my x-axis. This is my y-axis. For this first equation, or inequality, sorry, when x is 0, y is going to be 4. And when y is 0, x is going to be 6. So I'll go ahead and plot those 2 points down. X is 0, y is 1, 2, 3, and actually let me look at my other equation here. Maybe I want my scale to be a little bit different, but that'll be for my x-axis, so that's still fine. When x is 0, y is 4, and when y is 0, x is 6. So I'll just say this is 2, 4, 6. So this is 6, comma 0, and this is 0, comma 4. Those 2 points I'm going to go ahead and connect up with a solid line because this is greater than or equal to. So I'll go ahead and do that. Trying to be as exact as possible, but it's difficult. And while I'm here, I'm going to go ahead and pick a test point. The test point I'll pick is 0, 0. So I'm going to try this point right here and see if that point lands in my solution region. So if I do that, I'll get 0 plus 0, and I'm asking, is that greater than or equal to 12? Well, no, that's not greater than or equal to 12. 0 is definitely not greater than, nor is it equal to 12. So I'll shade the other side, not the 0, 0 side, but the other side, because 0, 0 is not a possibility for a solution. This is a quick little shading here, nothing really crazy. And now I'm going to go ahead and graph the other one. The other one, let's see, when x is 0, and maybe that color is not the best to use. Maybe I'll use red just because it's a little bit easier to see. When x is 0, y is a negative 5. And when y is 0, x is 12. Let's go ahead and graph those 2 points. 1, 2, 3, 4, 5. And 12, comma 0 is going to be, well, let's see, 2, 4, 6, 8, 10, 12. So I want to connect up those 2 points in red there, but this time with a dashed line, because this is not equal to, it's strictly less than. There's no equality there, so it gets a dashed line. I know I kind of bowed it there, but I didn't mean to do that. Anyway, I'll just make it worse if I try to fix it. Now let's pick a test point for this one as well. And again, 0, 0 is another good test point to pick for this one. So when I plug 0 in for x and 0 in for y, I get 0 is less than 60. Is that true? It sure is. So that 0, 0 is definitely in the solution set for the red inequality. So I'll go ahead and highlight that in there. And then you ask yourself, where are their shaded regions common? I'm still trying to dash this out. I'm having a hard time with it. Okay, so which regions are there dashed or their shadings common? It's pretty apparent it's going to be this region right here, but let me just number them anyway. This is 1, 2, 3, and 4. In region 1, only the purple is shaded there, not the red, so that's not worthy. In region 2, neither of them get any shading, so that's not worthy. In region 3, only the red gets shaded, but not the purple, so cross that out. But in region 4, they both get shaded. So region 4 is my solution region. Ugh, bad combination of colors. Really bad combination of colors. Anyway, that's my solution region right there. All of that stuff. So again, another example of actually a system of linear inequalities where one boundary line is solid and the other is dashed. Now, mathematics means little to most people unless you can apply it. So let's go ahead and do an application here. A home-based company produces both hand-knitted scarves and sweaters. The scarves take 2 hours of labor to produce, and the sweaters take 14 hours. They're just a larger, more difficult object. The labor available is limited to 40 hours per week, and the total production capacity is 5 items per week. Write a system of inequalities representing the situation where x is the number of scarves and y is the number of sweaters. All right. Well, I happen to know that it takes 2 hours to produce a scarf. So if I produce one scarf, it took 2 hours. If I produce two scarves, it took 4 hours. If I produce three scarves, it takes 6 hours. And if I produce X scarves, it'll take 2X hours. Sweaters take 14 hours each. So if I produce one of them, it takes 14 hours. Two of them, it takes 2 times 14 hours. Three of them, it takes 3 times 14 hours. Y of them, it takes Y times 14 hours. And we know that the sum of this time, the time that I take making scarves and the time that I take making sweaters, needs to be less than or possibly equal to 40. We're limited to 40, so we can go all the way up to 40 hours per week, but we can't go any more than that. Now, with that sentence, you should realize that linear inequalities really are what we deal with in regular life, not linear equalities. People don't want to work exactly 40. They'll work underneath 40 hours if they can. Or you might have to say, listen, I need to make at least $35,000 a year to afford whatever. Okay? So that's one inequality in this situation. And now we'll have another inequality here from the fact that our capacity, in other words, the majority or the most that we can make, most number of items we can make is 5. In other words, the combination of scarves and sweaters has to be less than 5, less than or equal to 5. So if I can make 5 scarves and no sweaters, or I can make 5 sweaters and no scarves, or some combination therein. And this is our system of linear inequalities. Let's go ahead and graph this so that we can see. There's no traditional solution that you'll know of right now to this. There are ways in the future you can learn how to find the best, the optimal combinations and stuff like that. But that's, of course, like linear programming is what they call that. And that's a little bit beyond the scope, or far beyond the scope of what we're going to deal with here. So let's go ahead and find out the intercepts here. When x is 0 for that first equation, y is going to be 14 over 40, which is 20 over 7. And when y is 0, x is going to be, 2 times 20. There we go. So I'll go ahead and plot those points. 20 comma 0. Let's just pretend that's about right out here. And then 0 comma 27ths. It's a little bit less than 3, so I'll just pretend it's right about here. So that's 0 comma 27ths. And now we need to connect those points, and it says we can be equal to them, so we'll go ahead and do a solid line. It's not too bad. There's something subtle here, by the way, so do not just walk away and go, okay, I know what's going on now. There's something subtle that's about to happen. Pick a test point. 0, 0 is a great one, right? Because it doesn't exist on our line. If you pick 0, 0, you'll get the following, that 0 is less than or equal to 40. That is true, so you can shade that side. And just wait for it. I'm almost done. I just want to show you something. Okay, let's graph the other inequality. The other inequality, when x is 0, y will be 5, and when y is 0, x will be 5. So I have something like, let me graph this in red. Something like this. 0 comma 5, 5 comma 0. And again, we can be equal to this line, so we'll go ahead and make this solid. Pick a test point and you'll find out that you're going to shade the side that has 0, 0 on it. Now you might think that you're done, but you're actually not. For real world situations, there's always, almost always I should say, two linear inequalities that are hidden in the word problem itself. Those two linear inequalities are the fact that, well, the number of sweaters that I make can't be negative. It has to be greater than or equal to 0. sorry, those are scarves, the number of scarves. But the same thing with the number of sweaters. They also have to be greater than 0. So I'll graph the line x equals 0, and that happens to be this vertical line that is on the y-axis here. And I'm going to shade everything that's greater than that, all the x values that are greater than 0. So it starts to get kind of messy. And finally, and I'll do this in orange, which will be very, maybe I'll do it in purple, bright purple. Finally, I'll graph y equals 0, which is a horizontal line at the x-axis. And I'll shade everything that's above that. Because again, you need a positive number of sweaters, or a non-negative number of sweaters. You can have 0, but you just can't have a negative number of sweaters. Now you have quite a few regions here, but there's only one region that has a common shading, where green, red, purple, and blue shade, and that's this region in here. So let me just go ahead and pick a harmless color like yellow for the shading. Okay. So this region right here is the common region. What's very important to note is that you always have to have, for real world situations, this realistic situation where the inputs, the x and y values, the number of sweaters you make and the number of scarves you make, can't be negative. That just happens in the real world. So they're part of your constraints. And as a final note here, you can have a system of linear inequalities that has 5, 6, 7 inequalities. Okay? It can happen. All you do is graph each of them, shade the sides that the test point works with, shade the opposite side if the test point doesn't work, go through and do their shadings, and then the area with the common shading for all of them is the solution region. Any point in that solution region will work as part of your solution. So this point right here, or this point right here, or this point, or even the points on the edges here, are all values of x and y that work with this situation. In other words, that we're working less than 40 hours a week and we're making less than or equal to 5 items per week. Okay. But anything outside of the shading, we're either working too much or we're making too many items. All right. That's it for this lecture.